The dot product plays a key role in the geometry underlying linear algebra. First of all, in a chosen basis, we can write vectors v and w in terms of that basis using coefficients v1 through vn. If we write those coefficients in columns, as we traditionally do, or by taking the transpose writing them in rows, the dot product reveals itself as a form of matrix multiplication, taking the corresponding terms of the two vectors and multiplying them together, then adding the sum. Moreover, through these two well-known formulas, the dot product reveals itself as encompassing all of our classical notions of geometry because it represents both length and angle in Euclidean space. Therefore, essentially all of classical Euclidean geometry is included in this little dot. Now you know that a square matrix, A, can be represented or interpreted as a homomorphism from Rn to Rn, if it's an n by n square matrix. Moreover, if the determinant of A is non-zero, the matrix is non-singular, and so we can think of it as an isomorphism from Rn to Rn. Now, isomorphisms preserve the entire space as a whole, but there's no guarantee that they preserve any geometry whatsoever. Therefore, we might reasonably ask, which isomorphisms preserve the geometry of the dot product? After all, if the following holds, that AV dot AW is equal to V dot W for all V and W in the space, then we can reasonably say that A preserves the geometry induced by the dot product. It preserves both our notion of length, because the length of V will match the length of AV, and it preserves the notion of angle, because the angle between V and W will match the angle from AV to AW. So let's find those isomorphisms that preserve the dot product and therefore that preserve geometry. Suppose that AV dot AW equals V dot W for all V and W. Using our transpose matrix product form, we can write this as V transpose A W equals V transpose W for all V and W. Now this is particularly interesting because this is a condition on the matrix A. To see this more explicitly, consider the case where V is the ith basis vector. In other words, the column vector V has a 1 in the ith spot and zeros elsewhere, and where W is EJ. So W has a 1 in the jth spot and zeros elsewhere. In that case, of course, the right-hand side is V transpose W is 1 if I is equal to j, and 0 otherwise. In other words, as a function of V and W, this is effectively the identity matrix. Let's write delta ij, sometimes called the Kronecker delta, for the function which is 1 if I equals j and 0 otherwise. If we interpret delta ij as being a matrix, then this is, of course, the identity matrix. It's the matrix whose ijth entry is 1 if I and j are the same, and is 0 otherwise. Okay, so here we are. We have the expression that EI A transpose A EJ is equal to the identity matrix on ij. If you pick that apart a bit, this is really saying that A transpose A is equal to I. To confirm that, think about expanding A transpose A using indices. If you say take the KL entry of A transpose and the LM entry of A and expand this entire sum using all those indices, you can see that by picking out the ijth entry here, you're getting A transpose A as the identity matrix. Therefore, since determinant of A is non-zero, and we already know that A has an inverse, therefore, it must be that A transpose is A inverse. So here's our definition. The orthogonal matrices are those satisfying A transpose equals A inverse and determinant of A is not equal to 0. Of course, the second condition is actually implied by the first once you say that A inverse exists. This is often written as O of n. Orthogonal matrices, those that preserve geometry. Via the dot product.